So is this proportions or means? Yeah, absolutely. How do you know that?
Equals percent.
There's percents and stuff in there. The type of data they gave us was this many students out of the total number have at least one tattoo. So it's definitely proportions. And again, making that choice tells us that we're going to revolve our hypothesis statements around P, right? So don't put a mu in there, put a P. And the status quo kind of idea or some prior knowledge goes in the first one. And what does she know about, or what do they know about tattoos?
23% American University undergrads have at least one.
Yes, and this isn't American, so a student asked me this earlier, this isn't the American university, this is just general American universities. Good question, if you read it quickly another way, you can think of it. So this is the sort of the status quo, the information she has, and she's thinking it's changed, but she hasn't made up her mind as to whether it's increased or decreased.
Doesn't equal.
Not equal to. And again, you use the same proportion here, the 0.23. Just like that, we're done with the first step. The second step is conditions and assumptions. See if we can go through these quickly. I'll paraphrase: random sample RS, independence, we're going to ask about that. We're going to check success failure, and we'll think about the 10% condition. So did she use a random sample?
Yes.
Good. She must have had a stat class before. Independence? I think each person's choice of being tattooed or not is independent of the next. Success failure. The total number of students she ended up asking, I need that N for this. I need to check.
235 versus 790. Oh, okay.
So what was N?
I think it was 235. Or wait a minute.
1026.
1,026.
Oh,
That,
sorry.
yeah.
I'm giving you the answer.
That's okay. Times 0.23. And then we have 1,026. Now, what percent of students did not have at least one tattoo? That's what Q is. 77%. Now, I'm not even actually going to calculate them, although I could, because these are such big N's, and roughly a quarter of that would be well over 10. And 3/4, I'm kind of doing some estimation in my mind, but I won't waste the time. Those are both at least 10. Now here's the 10% condition. She has 1,026 in her sample. Remember, we multiply it times 10, and we get 10,260 students. Are there more than 10,260 university students in the U.S.? Absolutely. What does this tell us?
We can use normal.
Use the normal model. Excellent. I'm going to. This is the last one I'm going to draw out for proportions. And then from here on out, I'll probably just use StatCrunch. So what goes underneath the middle of this distribution?
P.
P. So that 23% or 0.23. I'm going to use that same P to determine the standard deviation. And the 77% that don't have at least one tattoo. And our sample size of just over 1,000. And we'll get our measure sort of a spread here. Anybody want to tell me what that is? See some people.
.0131.
Yep. I'm gonna go out to 3 decimal places, 0, 1, 3, if you don't mind. But you could go more if you like, it wouldn't hurt. So I'm going to, because I hadn't even, notice I haven't even looked at the evidence yet. All of this has been set up with the mindfulness of the hypothesis statements. I haven't even looked at our sample, other than using the fact that there were 1,026 students. So I'm going to label both sides because I don't really have a direction here or even a intuition of where this is going to fall. So I'm going to add 0.013, so 0.243, 0.256, 0.269. I'm going to go backwards. Ooh. I might have y'all help me on this one. I hate subtracting decimals.
0.1.
0.
217.
217. 0.214.
204.
Yeah, that's right. 0.191.
191.
Good. So there's the entire model with this assumption that the null is true. So still doesn't matter if we have a not equals to in the alternative, a greater than or a less than, the null is always considered to be true. Now here's where the evidence comes in. We have a p hat, which again I haven't even computed yet. I do remember that there was 1,026 students. How many had at least one tattoo?
272.
All right, so if we divide that out, give me out to a few decimal points, what that works out to be?
0.27?
0. What?
265.
265, 27. I'm okay with either one. My theme has been 3 decimal value. I'm just going to stick with that. So here it is. That's the evidence that the researcher collected in recent times. So where does that fall along the number line?
Just before 0.269?
Yeah, just somewhere out here. So we can see generally where it falls. And after we draw these, we tend to do a little bit of shading because I'm really focused in on the probability. I mean, I can see right now it's over 2 standard deviations away. I'm already going, this is kind of unusual, right? Unusually high. But we're going to make our decision based off of a probability using our decision criteria. So I'm going to go ahead and shade to the right. What's the probability we got something as far away as we did or even more extreme?
0.265.
So we're also going to go, we're almost there, but I have to consider, she didn't decide, it's a she, right? I believe it says she. She didn't commit to a direction here. She didn't say greater than or less than. She just simply said not equal to. So we have to consider that this proportion that we observe could deviate this much to the right, or it could deviate, and notice I'm not measuring anything here. My curve isn't the most symmetric looking thing, but it could deviate that same amount to the left. And this is what a not equals to does for us in a hypothesis statement when it's the alternative. It forces us to think, well, that deviation could have occurred on the high side, on the overside of our mean, or it could be on the underside. So we have 2 tails, and again, my intention is not to label this, it's just to put it essentially in the same spot out. Probably a little better. And see that I have 2 identical tails here. Yes?
So could you not just subtract 0.269 from the 0.265 distance and then do that for the other side?
Absolutely. So we have 2 different tails to contend with. So this is the one we have the most information with. Let's start with that one, as Omar said. So we'll say Z, this is our Z-score, is the 0.265. Minus the mean, which is 0.23 in the center, divide by your standard deviation, and we get
0.132?
Why? It's going to be 2 point something. See how I know that?
2.69.
1, 2, and again, we're enumerating tick marks here.
2.692.
Yeah, 2.69. Now, is that plus and minus?
Yeah, you can think about it. If you're 2.69 standard deviations to the right, that same number, which we don't really have to know what that proportion is, if it were going to create a mirror image, would be 2.69 standard deviations to the left.
Okay.
Now, let's figure out what this area is. So we have to look up in our z-table. And when you look it up, if you look up 2.69 just as it is, it spits out a 0. Probably pretty high, 9, I'm going to guess.
0.9964.
Excellent, 0.9964. Now that's all the area to the left of this red arrow I drew here. So in order to figure out what's in the right, what do? We do 1. And so that area to the right there is 0.0036. That's what's in this little, it's a very, very tiny probability, right? Itty bitty. 0.0036. Now, we're assuming that we track the same area over here, so we can also assume that this is what? 0.36. So our p-value, our probability value that we're going to use to make our decision, that's why I'm so focused on it, is equal to 2 times 0.0036, because we have these two identical tails. The evidence gives me the means to figure out what the actual value or the size of this shaded area is, and then I just double it because of the aspect of it being two-tailed. So this is 0.0072. And you probably already had an idea of how you felt about this when you saw that when we drew the picture and the evidence ended up so far out. Your instinct is we're going to do what? Is the null hypothesis going to survive? No, we're going to reject it. But we still, now we have the probability value that will allow us to do that. So I guess if you're thinking about it, this extreme value, this 26.5% of students in this current sample that she had reporting a tattoo, or at least one tattoo. The likelihood that this would show up just due to chance, because again, we're under the assumption the null is true, would only be, what, 72 times out of 10,000? 72 out of 10,000, that's what, because we see the tenths, hundreds, thousands, 10,000s place. That's a really rare occurrence. So we're assuming that, it did happen, right? She didn't make it up. This is what she observed. There's a really great sample. That what that does is contradict the truth of the null hypothesis. We saw such a rare event. So I guess it comes down to step 4. What's your probability value? You can rewrite it down. Do I have an alpha for this one? I don't think I did I?
No.
Let's choose an alpha of 0.01. And any kind of exercise I would give you in class, not in class, on a test or in a homework, I tend to give the alphas. So again, I just inserted that just now. It really doesn't matter pretty much what alpha we've chosen of our traditional ones. This one's going to be what? Our p-value?
P-value is less than alpha.
Less than alpha. And that's the case if the p is extremely small or at smaller than the alpha. Our decision criteria told us we were to do what?
Reject. The null.
Reject the null hypothesis. So I can come over here in my dramatic fashion and disqualify it, right? It's no longer true.
Or null hypothesis.
So, what are we left with? We're left, the only thing we have is the only other hypothesis we have says that the proportion of American students that have a tattoo is not 23% anymore. So it would be a nice sentence since you guys write so much better than I do. I tend to start it with the sample evidence or the sample data because we're deciding this all off of the evidence we have. The sample data, what is it telling us? Suggest. I like that word, right? Nice. What is it suggesting?
That the number of American University undergraduate students with at least one tattoo. How do you answer that? Is more or less than? Or is not?
Yeah. Are there 2 T's in tattoo? Yeah, the TTOO. Or you could say the sample data suggests that the percentage of American undergraduates with at least one tattoo has changed. That would be acceptable. So that's sort of the lingering question they left us with: is, has this changed? Now, we didn't test. Our alternative was not a greater than. Our alternative was a not equals to. She didn't commit to a direction. So I can't say that it has increased, because that's not what I test. If I wanted to test that, I'd have to come back and change my alternative to be greater than, et cetera, and work on it. I have a feeling we'd probably come to the same conclusion, but because that's our alternative, that's the most I can say here in my statement. That's what we formulated. This is called a two-tailed test. Can you see why it's called a two-tailed test? And the two-tailed test nature of this comes from the alternative. If you look at our first question we did about car crashes involving cell phones, I call that a right-tailed test. If you can peek at my bell curve I drew, I shaded to the right, because it was a greater than as the alternative. The second question we worked with their concern about the proportion or percent of students who can finish college in 4 years. They were concerned that it had decreased. I call that a left-tailed test. If you look at the bell curve I drew on that one, when we put the shading in, when the evidence was put into the model, we shaded to the left. And then, of course, this one, two-tailed test. So in a left-tailed test, the probability value is really easy. You know, if you go to the z-score table, you can just pull it right out, you're done. In a right-tailed test, we learned that we had to do 1 minus. And that's just that sort of skills you've developed about how to use the z-score table, or z-table. In a two-tailed test, you have to be mindful to whatever probability you find, whether the evidence ends up on the top side or the bottom side, you have to be mindful to double it. And it gives you the right probability value to test against your significance.